I hope you are all doing very well, and welcome to the semester. I hope we will have a good class in thermodynamics. And today is the first lecture, so probably you are excited about what thermodynamics is, energy is, whatever. So I will try to give you an overview today as to what thermodynamics is. And we will do this course as a team together with Demiral Hoca and also Mehmet Can as the assistant. So you will have, I think, a good team here to help you learn thermodynamics and to master it. I will probably do most of the lectures, and Mehmet Can will do the problem solving. But I am available to answer your questions all the time. And I am sure you received the course syllabus. It has all the details about the course. So I ask you to go through the syllabus. And everybody will have to get the ebook because there is no other way to make this course, I think, effective. The books are usually expensive, but the ebooks are reasonable. So I ask you to take care of the book this week so that you can start reading the current chapter and the next chapter also, so that we can learn effectively all together. And before I start the material, what I would like to do is give you an overview as to what thermodynamics is. Okay, and if I can get the presentation up. Let me see. And sometimes technology plays tricks on you. Okay, do you see the PowerPoint file?
Yes, we can see.
Okay, excellent. Okay, do you have any idea what thermodynamics is? Maybe you heard the name. Well, this is what you are here to learn, right? But thermodynamics is basically about energy. It is about anything and everything about energy. Therefore, thermodynamics is the science of energy. So I am sure you know a lot about energy because everybody speaks about the energy, the prices, and the energy wars, energy forms, natural gas, electricity, whatever. But the difference that you will acquire in this course is you will be a knowledgeable person in energy. That is, you will know what energy is, how to deal with energy, and to really be able to make calculations, to have a deeper understanding of energy. And you can do it only if you have a good understanding of thermodynamics. Therefore, thermodynamics is basically about the basic principles of energy. That is to understand what energy is. And it is not a surface or superficial understanding. We have to have some intuitive understanding of energy, and especially the conservation of energy, conversion of energy, and transfer of energy. And the course will not be just a theory. it will have to involve a lot of applications from the real world, and it is what we will do. And we will learn about efficiency and effectiveness. Okay. And this is the book that we will be using. It is the 9th edition, SI version. The book has 17 chapters, and we will cover only 8 chapters in this course. And those of you who continue on taking Thermo 2 will go through the rest of the chapters. And today, we will go through chapter 1 today, the basic concepts. We will learn about the vocabulary of thermodynamics. And next week, we will start chapter 2. But as you see from here, basically, we will learn about energy, the general energy analysis, and then properties of substances. And then we will simply do energy analysis for closed systems. We will discuss it in a few minutes, and control volumes. And then we will do the second law of thermodynamics, which is more interesting and intriguing in chapters 6, 7, and 8. So this way, hopefully you will have a very good grounding in thermodynamics. Now, if you ask me to summarize the basics of thermodynamics, I think what you see on the screen gives a good summary. Basically, 4 principles. The mass balance, conservation of mass, and you know that already from high school and from physics courses. That is, mass change is mass transfer. Whatever mass is entering and then mass is leaving from a system is the change in the mass of the system. Just pure logic. Same goes with energy. Okay, energy balance. It is conservation of energy. Again, you have a system and you have the energy input, energy entering the system. This is by heat, work, and mass. And then energy leaving the system. The difference is the energy change of the system. Again, nothing unusual, right? You know this from physics. Now, what you don't know is probably entropy and exergy. So they are properties associated with the second law of thermodynamics. Here, entropy and exergy are not conserved. Entropy is generated. You see the entropy generation term here, okay? And exergy is destroyed. And here you see the exergy destruction term. So they are different from the mass and energy. It is the reason that some people have difficulty sometimes understanding entropy and exergy there. But when we get to it, you will see that it is not really that hard. So don't worry about it. If again, compare the first and the second laws of thermodynamics, the first law deals with conserved quantities, matter and energy. This is what we will do in the first half of the course, and deals with physical quantities. They can be perceived by the 5 senses, and it closes the door to the perpetual motion machines. That is, the claimed machines that create energy out of nothing. There are no such machines. And the first law kind of makes sure that you don't fall for such claims. And the second law deals with non-conserved quantities like entropy and exergy. And it deals with things that go into non-existence or they exist out of nothing, unlike mass and energy. And the utility of the main utility of the second law is that it establishes the metrics to quantify waste and to assess the degree of perfection. So they are kind of, vague terms right now, but you will see the value later on. And we will have efficiency, 2 kinds. The first of efficiency, we will start doing that in chapter 2. It is the degree of completion of energy transfer or transformation process. If there is a complete transfer or transformation or conversion, the efficiency is 100%. And the second law of efficiency it is a measure of perfection. That is, if something has, a process has a second law efficiency of 100%, it means the efficiency is this, that process is perfect. Okay, so we will define perfection from the second law point of view. Now, to represent them graphically, okay, as the three legs of thermodynamics, the first leg is conservation of mass and conservation of energy. Again, the things that you are familiar with. The second leg is effectiveness. That is, we want to use all the resources, the energy sources effectively, and efficiency. That is, we want to have the highest possible efficiency. And the end result is, as you see here, zero waste. That is, ideally, we should have zero waste or perfection, because if there is zero waste for a process, that process is thermodynamically perfect. Okay, and we cannot achieve it in the real world, but we can come close to it, and we can kind of see how close we are to perfection. Okay, some examples. I'm sure you hear about some cars going uphill. If there are any among you from Erzurum, probably you remember the Abdurrahman Gazi hill there, right? You turn the engine off and the car goes uphill, supposedly. And of course, everyone is amazed, and they claim this violates the conservation of energy because the car is going uphill and gaining potential energy, okay, without any energy input because the engine is not working there. It looks that way, and if it were true, you wouldn't be taking this course. That is, thermodynamics wouldn't be a science anymore. But if you take a water level meter, as you see here, okay, I was in Erzurum and they told me that cars go uphill. I said, well, that is easy to check. So I asked them to bring a water level meter. And then when you put this, on the ground here, you clearly see that what looks to the eye as uphill road is actually downhill. Okay. Therefore, the eye sometimes can be deceiving. So what you see may not be correct because of the topography of the geography there. Okay. What is actually downhill may appear to the eye as uphill. Therefore, even if let's say we see things that may confuse us, we know that the laws of thermodynamics still prevail. Okay, here's a question for you. Okay, we know that the refrigerator cools the air inside. Now, let's say it is hot and you open the door of the refrigerator like this, okay? You will see that cool air is, rushing out. And imagine the refrigerator is in a sealed room. Now, what do you think will happen? And this is continuously running. Will the room get warmer or will it get cooler? Okay, think about it for a minute. Okay, probably some of you are thinking that it will get cooler because of this cool air. But thermodynamics says that, look at the wall outlet here. This refrigerator is continually consuming electric power. And then we ask, what happens to this electric power, this electrical energy? It is not anywhere in that room anymore. So, okay, it went to the motor of the refrigerator, to overcome the frictions. And then at the end, the whole thing is converted to kinetic energy of materials, air, whatever. All will show up as heat. That is, all the energy consumed as electricity eventually will have to show up as another form of energy, which is heat. As a result, the temperature in the room will have to rise. Okay? So this is, the thermodynamically viewing things. That is, we take the principle of conservation of energy and the energy conversion, the forms of energy, and then we can answer such questions authoritatively, without any doubt. Okay, maybe you heard about Hyperloop. Okay, Elon Musk, one of the crazy projects there. A tunnel between San Francisco and Los Angeles in California. And the tunnel is evacuated. Now the question is, what is the minimum amount of energy needed to go from San Francisco to Los Angeles? Now think about it for a minute. That is, you are in San Francisco and you go to Los Angeles with this train here in this Hyperloop. Now normally, and it goes like very fast. And maybe in 1 or 2 hours, it can go to Los Angeles from San Francisco. Normally, you will think that you will need a lot of energy, but from a thermodynamic point of view. Now, let's say you start here at 0 velocity at sea level, and you end up here again at 0 velocity at sea level. That means the contents of the wagons, the trains, did not experience any net energy change. Okay, and neither the train did. That means there is no energy that shows up somewhere. And if, let's say, this is perfectly evacuated so that there is no air friction, now that means the minimum energy unit is 0. You don't need any energy. Then you may ask, how can I accelerate it? Well, what you can do is, you can have a spring here at the very beginning, okay? And the spring is compressed. Imagine like it pushes the train, okay, to accelerate it. And then when it comes to Los Angeles, okay, there is this spring again. It compresses the spring and stores that energy back, okay? And this can just, repeat itself. That is thermodynamically, if everything is perfect, this train can run like forever, but of course things are not perfect. But it shows that at least the amount of energy needed will not be very much there because of the friction being limited. Okay, here is another question. It is a very difficult question. What is 2 plus 2? Of course, you are laughing. Everyone knows that, right? It is 4. Now, the first one will say you that yes, 2 plus 2 is 4. But this is true for conserved quantities like mass and energy. Now, the second law says, well, it may be 4, it may be 0, it may be 7. Why? Because the second law doesn't deal with conserved properties. So the understanding of the second law gives you another dimension in thinking. They are things that go into non-existence, unlike mass and energy, and they are things that are created out of nothing. Second law deals with such quantities. Now, to make you understand, okay, everyone knows this phrase, right? Unity is a source of strength. But is it really? As you get united, do you get stronger? The first law says yes, because you have more resources, more people, more money, I don't know, more everything. So you are bigger, you are stronger. The second law says, it is the case many times, but not always. Sometimes unity can be a source of weakness, which may sound strange to you. If you don't believe me, look at some marriages. They are united, but you can see what happens to them. Some companies, they merge, assuming that they get stronger, and then they collapse because it wasn't the right merger there, etc. And the second law helps you analyze these things. When it is good to be united, when it is good to be not united or not to merge. We will show this with numbers. And if you compare the efficiencies of the first law and the second law, the first law efficiency is the level of performance achieved compared to the resources consumed. But the second law is the level of performance achieved compared to the best possible performance. That is, you compare the actual performance to the best possible performance under the same circumstances. And the end result is, of course, perfection there. And just to give a couple of examples on this. For example, as students and we as workers, what is our second law of efficiency? Okay. Now, as a student, you will spend a lot of time, right, studying for courses, getting good grades, learning whatever. And what is your efficiency? It is the things, your actual performance, as we can see from grades, skills acquired, tangible outcomes produced, compared to the best possible performance under the same circumstances with the same resources. Okay, so this is the second law of efficiency. That means using the same time, the same resources, if you can produce more, okay, then probably you will have a better, higher second law of efficiency, and you will be a better performer there. Example, commuting. Let's say you go to work or to school or to other places using public transportation. It looks like, well, you are just, on the road, nothing to do. So it takes half an hour, 20 minutes, whatever, and you don't feel bad about it because you use that time to go from point A to point B. But if you look at it from another perspective, for example, what happened to your intellectual capacity? That is, obviously, you don't need to utilize it during transportation. It is not part of, walking, but you certainly can read a book, okay, can maybe answer your emails, or you can even learn a language during that transportation. That is, you can utilize your intellectual capacity. Now, the question, is it utilized or is it wasted? Okay, if you wasted it, although it doesn't look like you are wasting something, a resource, but you are wasting your intellectual capacity. Now, to give an example from myself, I went to school when I was your age as students to Istanbul Technical University in Istanbul, and the instruction was Turkish, but I learned English in public transportation. That is, as I went from our house to the university and back in the evening, all I did in the buses, İETT, okay, just prepare notes for English and practice it and learn English. That is the time that would be wasted, or the intellectual capacity, that way can be used. And you feel better because you utilize your capacity there. Otherwise, you feel bored. Okay, and same goes with emotional capacities. Same goes with social capacities, other things. So we are wasting a lot of things without even noticing it. Now let's look at the history. Okay, I'm sure you know about the steam engines, right? It is how the Industrial Revolution started in England in 1700s and 1800s. And you will ask now, okay, what is the connection between steam engines and thermodynamics? The history of steam engines is really the history of thermodynamics. That is, before the steam engines, there was no such thing as thermodynamics. Although we had architecture and then some other things, but machinery-wise, converting heat to power, okay, motive power, it happened with steam engines. And the funny thing is, no one knew anything about thermodynamics. What is the result? It was just trial and error because you don't know basic principles. Now, some people think that, well, you know, the courses are just theory. The important thing is practice. It is not really exactly true. If they knew about thermodynamics, advancing the steam engines would probably take a fraction of the time instead of taking more than, what, 150 years to reach, you know, some reasonable level. Initially, their efficiency was like 2%, okay? And after years of improvements, it went up to 4%. Nowadays, heat engines have efficiencies like 40, 50%. Why? Because we know thermodynamics and we know how we can improve performance here. Therefore, if you look at the history of Industrial Revolution, study it and examine, you know, what went on there, what they tried, what worked, what not worked, and the kinds of theories that they developed, you are really studying thermodynamics, which is fascinating. There are a lot of books for reading if you have time later on. Okay, now let me take a little break here and ask you if you have any questions so far. And you can unmute your microphone, ask the question, and then mute your microphone again. Does anyone have any questions so far? Okay, no questions. So that means we will continue. Okay, now let's get into energy. Again, we are simply exploring. We haven't started chapter 1 yet. Okay, just kind of, you know, preparing you mentally to the study of thermodynamics. For example, solar energy and nuclear energy. Probably you know that if you ask people about solar energy, almost everyone will say, oh, it is great, nice, clean energy. It is renewable, so we should be using a lot of solar energy. And ask them about nuclear energy. Oh, it is bad, it has radiation, it causes cancer, it can kill people, whatever. What is the funny thing here? The solar energy is actually nuclear energy. That is, the sun is a nuclear power plant. There are nuclear reactions going on. The difference is when you use uranium or thorium, it is fusion. It is a fission. Kind of you split the atom. In the sun, we have two hydrogen fusing into a helium. But again, both are nuclear reactions, and the sun also has radiation. If you have, let's say, if you know people with skin cancer, the #1 cause is this radiation from the sun. It is the reason that they are asking you to use sun blocking creams, and thousands of people in the world die from skin cancer every year because of exposure to solar light rays there. But somehow, you know, no one talks about it. Again, this is kind of, we are conditioned to think that solar is good, nuclear is bad, whereas solar is actually nuclear. Okay, now you also know the hydropower, hydroelectric power plants on the rivers, lakes. In Turkey, we have a lot of them, and also in, let's say, Brazil has a lot. Northern European countries like Norway, a lot. And we think that it is the energy of the water. Well, if you think again deeply, it is actually solar energy. Why? Because once the water, okay, flows down to a low level, you cannot reuse it unless it goes up again. Okay, and how does it go up? Let's say it went to the sea, ocean, lake, whatever. It has to evaporate. So the solar energy does that. And then it has to come down as rain to high elevations or snow. and then as it flows down, you can capture that potential energy. Okay, so you have different, energy transformations here, but what is the end result? The hydroelectric power is actually solar energy. Same goes with our fossil fuels. Now, right now we say coal is bad because it pollutes air, petroleum, natural gas, whatever fossil fuels. So we should stay away from them, right? But keep in mind that all the fossil fuels, they formed from plants, animals, whatever. They are organic, okay? And their energy originally came from the sun. That is, all the plants, they have bioenergy, and the source of that energy is the solar energy. If there is no sun, no plant can grow. So actually, I think the coal that you see here is actually part of solar energy there. Okay. And biochemical energy. Let's say we eat plants and we energize our body. Again, all these cherries or whatever, okay, they come from the sun. So we are actually eating solar energy. Without the sun, you cannot have any plants. Without plants, you cannot have any animals. And without plants and animals, we cannot eat anything. So that means there would be no life there. And another interesting thing is, we think that we have the body heat to keep us warm, but actually we are, as human bodies, combined heat and power. That is, our body produces heat as well as power, the muscle power. In thermodynamics, we call them combined heat and power system or cogeneration systems. They are, nice applications because using coal or natural gas, you can produce electricity as well as heat, and usually it is very economical then. And on perpetual motion machines that I mentioned, okay, I think they are the most striking examples because they violate the conservation of energy or the first law of thermodynamics, okay. And so to understand the first law, a few examples of perpetual motion machines will be, I think, very good. These are nothing new. For example, this magazine is like almost 100 years old, and you can see they are talking about the perpetual motion machines even at that time. Okay, that is creating energy without using any energy. How can that happen? Okay, look at this wheel. You know from physics that moment is force times moment arm, right? Now here, on this part, the moment arm is long, so you can imagine that it will give you a large moment, or here. And here the moment arm is short in the middle part, okay? And that difference should create some turning power, but it doesn't work that way. If it worked, it would be creating energy. And the first law says that cannot happen. So it is in the museum, as you see here. People thought that it should work, but it doesn't work. Again, the same idea. Again, this is, the weight, the force here. Compare it, let's say, the moment that this force will create. And you can see the difference, okay? This is the moment arm, that is the moment arm. This is much longer here. So this will have a larger moment here, since moment is, force times the distance there, okay? But when you put it to work, again, it doesn't work. If it worked, it would create energy. And thermodynamics says that cannot happen, okay? And many people, got patents for the perpetual motion machines. It dates back to like 1600s. People are receiving patents to protect their inventions. thinking that it may work. Okay, but none of them has ever worked, so it is safe to say that none of them will ever work. And one reason for this deception is, okay, remember the Pascal's law? Okay, here let's say you have a large cross-sectional area and a small cross-sectional area. If you apply a small force here, F1, the pressure will increase, right, at point 1. Now, what happens to pressure at point 2 right here? It is the same as 1, but the area is much larger. And what is the force? Force is pressure times the cross-sectional area, okay? That means using a small force, okay, you can apply a large force and you can lift heavy things. Many people take this as they are creating power, energy. They don't, okay? You can increase the force, but you cannot increase energy. The reason is, now this small piston, when it goes, let's say, imagine the area ratio is A2 over A1 is, let's say, 100, okay? When this piston goes down by 100 centimeters, this large system will go up by only 1 centimeter, okay? And what is energy? This force times distance, and the force times distance is the same in both cases. Force times distance here. Therefore, you are not really creating any energy, okay? But some people somehow confuse this, especially, let's say, magnets. They see there is a force there, and they think they can do a lot of things with that force. It doesn't work that way. Some people think about, let's say, using water, H2O, as fuel, because they look at the water and the gasoline, benzene, okay? They look the same. You cannot tell them apart. Then why do we, use gasoline, which is expensive, in our cars instead of water? Maybe we can just use water, right? Again, it doesn't work. Why? Because gasoline is a hydrocarbon, CnHm, and when it combines with oxygen, you end up with carbon dioxide plus water vapor, okay? And this releases this exothermic reaction, a lot of energy here. Okay, water. If you combine water with oxygen, what will happen? You try to burn it. Okay, what will happen? Nothing. Water cannot be burned. Why? Because water is already burned hydrogen. And all the energy to be produced is produced as hydrogen is burned. Therefore, what you can do is take this energy that you produce as you burn hydrogen, give it back to H2O. You can separate this, okay, into hydrogen and oxygen, and then you can use that hydrogen as a fuel, okay? But the amount of energy you get as you burn the hydrogen is the same as the amount of energy that you supply as you separate water into hydrogen and oxygen. Therefore, this law of physics, the conservation of energy, or the first law of thermodynamics, okay? It is solidly correct. So far, okay, there has been no violation of it, okay? Therefore, as engineers, future engineers, you should have no doubt, and you should close your ears to such claims. If perpetual motion machines were true, then we wouldn't have an energy problem. They always complain like they don't have enough investments, whatever. The thing is, if let's say you can do this, you will not need anything, because you can just go borrow the money and you can be a billionaire in a few months there. And an argument I often get is for the laws of thermodynamics. They say, well, in many things in the past that were impossible are now possible. Many things that couldn't be done in the past now can be done. So maybe the perpetual motion machines, okay, we couldn't do them in the past, but maybe we couldn't do it now. This is the argument I get. And my response is, if the reason such machines were not built in the past was the technology that is not having enough materials, technology, whatever, that can change. That is the things that cannot be done in the past because we don't have the technology, okay? They can be built today or tomorrow. But if the reason for them not being built is because they violate the laws of physics, okay, they can never be built. Because the laws of physics, they are valid today, they were valid yesterday, they will be with us again tomorrow. And conservation of energy, the first law of thermodynamics, is a law of physics. Therefore, even in the future, you can never build a machine that will generate energy. This is like, let's say in a basketball, okay? You have, let's say, 5-point difference, and there is only 1 second left. Now the question is, if you are 5 points behind, is it possible to win the game? What is the answer? It is impossible. Why not? Why that way? Because there is only 1 second left. That means you can have only one shot and you can get at most 3 points. That's it. Okay? And the difference will be 2. Again, you lose. Why? Because of the rules. If, let's say, you can change the rules, like you can make a score like 6 points with one shot, yeah, then okay, it is possible. But as long as the rules remain there, you cannot change it. In basketball, we can change it. It is in our hands. But in physics, changing the laws of physics, it is not in our hands. That is, human beings or any other creature cannot change the laws of physics. Okay, some ramifications of thermodynamics. You hear about sustainability a lot. Okay, sustainable future, sustainability in energy, whatever. And it is again related to thermodynamics. And at the end, you will have a better appreciation of sustainability in energy. If you break it down, it basically involves renewable energy. That is not the fossil fuels like coal, petroleum, natural gas. Energy efficiency. That is using the energy efficiently, minimizing waste. And right now, lately, storage. Because sometimes we generate so much renewable energy from the sun and wind that unless we can store it, we cannot use it. So these are the 3 legs of sustainability in energy: renewable energy, energy efficiency, and storage. And the way we utilize them and the result we get is simply low carbon dioxide generation, which is good for the planet because you will generate fewer greenhouse gases, and also the climate change, the global warming will be less. And how do we do this? Low carbon technologies. That is continually improving the technologies there. And technologies that you use, low carbon. And the Paris Agreement, it was signed in 2015. Some of you may remember that. It set a goal. And the goal is to limit the temperature rise of the planet Earth to below 2 degrees Celsius. Okay? In fact, ideally, below 1.5. And many countries signed this. So they are also following their energy use, their contribution, whatever. Okay. So this is like a global drive and global cooperation to limit the temperature rise by using renewable energy, energy efficiency and storage, and reducing the use of fossil fuels like coal, petroleum, and natural gas. And this sustainable development is, as a result, a concept of second law, because you can do it by minimizing waste. Energy efficiency is entirely minimizing waste, and so is renewable energy. Okay, and engineering ethics also closely related to that, because if you use a lot of fossil fuels right now, there will be less left for future generations, which is not ethical. And the second law helps us with this process because it is an effective tool to identify waste and also to point the direction of minimizing that waste there. And energy efficiency can be defined or described as the most domestic, cleanest, cheapest, most environment friendly, most accessible, and the largest energy source. Why largest? Because let's say our energy use is increasing by 3% every year. We can very easily save 3% of the energy that we are using. That means you are meeting your new energy needs simply using energy efficiency instead of building new power plants or mining new sources there. For example, lights, okay? By using LED lamps instead of the old incandescent lamps there, you can reduce your light energy usage to 1/5. That is 80% savings. They are more expensive at the beginning, but if you consider the lifetime, okay, you save a lot of money. And right now, you cannot buy the old type in many countries anyway. And let's say just one example from the United States, the refrigerators. In 1970s, a typical refrigerator used like 1,750 kilowatt hours of electricity. But in 2000s, it went down to about 500. And right now, it is probably 350 kilowatt hour per year. Okay. And as a result of this drop, okay, when you calculate the energy saved, it comes down to 30,000 megawatts of power plants, which is equivalent to like 30 nuclear power plants. Okay, just making refrigerators more energy efficient saves you 30 nuclear power plants or 60 coal power plants. So this shows the power of energy efficiency. And if you compare the savings, in 70s, I was a student in the US, and when I took a course on advanced energy systems, I remember this curve, that the energy use would increase as you see here like this, okay? Just continue increasing. Why? Because the population is increasing, economy is growing, and as a result, you need more energy. Then what happened in 1970s? We have the Arab petroleum embargo, the oil embargo. As a result, countries had to start saving energy. They started energy efficiency measures, developing new technologies. They did not want to be dependent on foreign oil. And you can see the change here. After 1970s, okay, what we have here is, instead of energy usage increasing, it is really remaining the same and increasing very mildly. And in 2003, normally the United States would spend like $1.7 trillion on energy if it did business as usual. But as a result of conservation measures, energy efficiency, it saved, this much energy. And for 1 year, like year 2003, the money spent on energy was only $1 trillion. What is the difference between the two? $700 billion energy saving per year. So it shows the power of energy efficiency. And thermodynamics shows you what can you do, how effective they are. And this way, I think you can do this scientifically and also economically. And renewable energy. For example, the wind is blowing. If you capture the kinetic energy of the wind, okay, then you can generate electricity here. But if you don't, the wind is just blowing here, that energy is eventually converted to heat, okay? The same with the sun. Let's say you have the solar energy here. If you use it, at least part of it, to convert to electricity and generate, so many kilowatt hours of electricity, then you save energy because now you need less coal or oil or natural gas. If you don't do this, what happens? It is converted to heat, so the planet is heated. Therefore, the whole thing is wasted. Therefore, what we should remember is unused renewable energy is wasted energy. So the second law teaches us or preaches us the best resource utilization. And it can be done by reducing waste, increasing effectiveness, and improving efficiency. That is how we can keep the planet Earth green and have a sustainable economy. Therefore, I hope at the end of the course, the main message you will get is how to reduce waste, how to be efficient, and how to be effective when it comes to energy. So this is the introduction. So I'll stop here for the first lecture. Now, before the break, if you have any questions, I will be glad to answer. Does anyone have any questions before the break?
Sure, I have a question.
Yeah, okay, go ahead.
We said we cannot burn water. So if we put some water drops to fire, the fire increases, right?
No, not necessarily.
So is the water behaves like fuel, or another things happen? Okay,
when you pour water into the fire, okay, if you pour a lot, the fire will be extinguished. So let's say we put only a little water. What happens is water evaporates, okay? It is converted from liquid to vapor. It is still H2O, except in the vapor phase instead of liquid. And water expands. When it expands, you can see kind of the fire, getting larger because something is expanding there. But it is simply the water, liquid water, being converted to vapor, and the vapor kind of moving the fire. It doesn't add any energy, and it is the reason that if you pour in more than the fire can evaporate, the fire will be extinguished. That is, the water does not burn, it cannot burn. If you put hydrogen in or natural gas, it will be a different story.
Okay.
Any other questions? Okay, if not, let's take a 5-minute break. Okay. And then after 5 minutes, we will meet again.